Let's take some time to go over acid and base. It's a very important topic for organic chemistry. So section 2.7 in your note packet and in your textbook starts talking about the Bronsted-Lowry definition of acid and base, that an acid is a species that loses a proton, a base gains a proton. And remember that a proton is the same as a hydrogen ion. Hydrogen atoms have one proton and one electron, and so when you have a positive one charge on a hydrogen, the electron is gone and all that is left is the proton. So these terms are interchangeable. Proton is a hydrogen with a positive charge. One thing we should be able to do is identify acids and bases when we see them in a equilibrium or in a reaction. So take a look at what is happening to this species as it goes to become this. And what is happening here is that this hydrogen ion is going away. So the H is missing, and then the charge has gone from being 0 to being -1. So H plus has gone away. So this species on the left is giving up a proton to become the species on the right. That makes this the acid. And the species on the right is the conjugate base. I'm just going to write base over here. This other molecule over here, going from the species on the left to the species on the right, has gained a proton. You'll notice the formula has gone from NH3 to NH4, so there's another H there. Also, the charge has gone from 0 to +1, so it's gained a H plus, a +1 charge, and another H. So that makes this a base. And the species on the right is the conjugate acid. And you know that this is an acid because if you do the reverse reaction, going from NH4 plus back to NH3, you lose a proton. So the acid, NH4 plus, loses a proton to become NH3. And in the reverse direction, C2H3O2 minus 1 charge becomes HC2H3O2 by gaining a proton. So the base going from right to left, so the reverse reaction going this direction, this is a base because it's gaining a proton. The conjugate acid-base pair is the same thing before and after losing a proton. So let me highlight these. One conjugate acid-base pair is ammonia and the ammonium ion, so that's one pair. And the other pair is this. This is acetic acid, and this is the acetate ion. If you remember from general chemistry, C2H3O2 with a -1 charge is the acetate ion. And this is acetic acid. A lot of times we write acids with the H that's able to be lost first at the beginning of the formula to show that this H is something that can be lost. The other three H's that are in the middle of the formula are not ones that can be lost. So I just want to go ahead and draw the structure of this compound. This is C2, there's two C's, an H3 over here and an H over here, and two O's. So this is the structure of acetic acid. And this H over here is the one that can be lost. It's part of carboxylic acid. The other three H's on this side are not ones that can fall off very easily. So we separate that out in the formula. Over here we have an important factoid to know, that the stronger the acid, the weaker its conjugate base. So if you have an acid that is really ready to give up a proton, then the base is not as ready to take it back. I sometimes make the comparison of an acid to a person that has money that they can lend to someone. So if you have some cash on you and then a friend of yours doesn't have anything and is hungry and needs some lunch, you could lend them some money. So in this case, the acid would be giving up a proton. You'd be giving up money to your friend to let them have some lunch. Once the money is gone, you cannot be a money lender anymore. So maybe if you start getting hungry, you're going to be a base and you're going to borrow some money from a different friend to be able to eat your own lunch. So once the acid has given up a proton, it doesn't have a proton to lose anymore, and so it is now a base. It is looking for a proton to take back from another species. Same thing with a base. Once a base has gained a proton and become the acid, now the acid has a proton that it can lose again. So just like a person can give up money and become, go from being a lender to being a borrower, a species can give up a proton and go from being an acid to being a base. Then we have this factoid that if some compound is a very strong acid, if it is really willing to give up a proton, it is not this compound that needs the proton back very much. Same kind of thing with a person lending money. Someone who lends money very easily is not the same kind of person that is very eager to take back the money. So someone who's very generous tends to not be very stingy, and vice versa. If some person is very kind of a money grabber, someone who's really very stingy and very tight with money, then they are not going to be willing to give up money very easily. So this is an important factoid to remember, that the stronger the acid, the weaker its conjugate base, because we're going to be talking about how strong acids are relative to each other, and usually it's easier to focus on the acid, and then the base can be figured out using this factoid over here. Let's go ahead and use this factoid to figure out this problem over here. We're going to try to figure out which one of these is a stronger base using the factoid that the stronger the acid, the weaker the conjugate base. Let's go ahead and identify these as acids and bases. So we have an acid-base equilibrium. We want to know which ones are the acids and which ones are the bases. So aniline, when it goes to become anilinium ion, what is happening? What is changing about it? It's going from this NH2 to an NH3 with a positive charge. So it is gaining a proton. That makes this a base. So going from the right to the left, it's losing a proton. That makes this an acid. Acids lose protons. Looking at the methyl ammonium ion, going from left to right, it is losing a proton. It's going from NH3 plus to NH2 with 0 charge. So that isn't what an acid does. Acids lose protons. Going in the opposite direction, it is gaining a proton, so that makes this a base. And when you do this, you should end up with one base and one acid on each side, because we have a base reacting with an acid, making the conjugate acid and the conjugate base. If you try to label these and you come up with 3 acids and 1 base, or both the acids on one side and both the base on the other, then you should take another look at what you've done. That's not correct. So now we have to figure out which one is stronger. This problem is telling us that the anilinium ion is a stronger acid. So the anilinium ion is one of the acids that we labeled. Let's label that as stronger. And then the other acid is the methyl ammonium ion. So that one is the weaker acid. And the factoid that we learned on the previous page was that the stronger acid has the weaker conjugate base. So the anilinium ion is stronger. That makes the conjugate base aniline weaker. This is a weaker base. And then in contrast, the weaker acid, methyl ammonium ion, gives the stronger conjugate base. So methylamine is the stronger conjugate base. So once you've labeled your acids stronger and weaker, you should find that both of the weaker are on one side and both of the stronger are on the other side. If you have one side with a weak and a strong and the other side with a weak and a strong, then you have not done it correctly. So go ahead and check that again. Once you've labeled all of these, when we do an equilibrium reaction, the weaker side is favored. So we're going to be doing this more with different reactions, different equilibria. So the weaker side would be the side that is favored. This particular question is just asking which is a stronger base. We've gone a little bit further than this specific question wanted. So the stronger base we have figured out is methylamine. That's the stronger base. It's a base and it's the stronger one. The other base, aniline, is the weaker base. So let's go ahead and highlight methylamine as being the stronger base. So this next problem, we don't have a reaction, we just have one substance here, HBr, and we want to have the conjugate base. So if you're being asked for the conjugate base, you know that this thing that you have is an acid. And to get from the acid to the conjugate base, we have to lose an H+, we have to lose a proton. And we have to only lose one of them. So some of these have two possible protons that can be lost. We're just going to lose one proton. When we lose a proton from HBr, we have Br, and it has a minus charge, -1 charge. Because we start off with HBr, which had the charge of 0, we lose a plus, that gives us Br with a minus. So you could write the 1 minus, or you could just write minus, either one. So for H2SO4 sulfuric acid, we want to lose one proton. Let's write that. If we lose one H+, what that gives us as the conjugate base is HSO4 with a -1 charge. The bisulfate ion, if you remember that from general chemistry. For acetic acid, we are also going to lose one proton, and that gives us the acetate ion, C2H3O2 with a -1 charge. So you could write one negative, or you could just write one negative line there. In a similar way, to get the conjugate acid of a base, so if you're being asked for the conjugate acid, then what you have is a base, and then to get the conjugate acid, we're going to gain one proton. When we gain one proton, the carbonate ion here, CO3 with a -2, becomes HCO3 with a -1. So we've gained an H, and we've also gained a +1 in the charge, going from -2 to -1. We've gone up by 1. -2, adding 1 to that gives us -1 as the charge. Bisulfate ion, HSO4 with a -1 charge. When we gain a proton, we end up with H2SO4 with 0 charge. We're going from -1, adding something to that gives us a 0 charge, H2SO4. A lot of times when we have amines here, we're going to learn that amines are organic bases. The lone pair on nitrogen tends to be able to attract a positively charged proton. So we're going to put the additional H+ onto this nitrogen. Instead of NH2, this nitrogen is going to have 3 hydrogens, and we're going to have a positive charge. So we're gaining one proton again, and that gives us this formula over here. The nitrogen is the atom that has gained a proton, and then we can't forget the positive charge because we have we've gained a +1 charge starting with 0, so we end up with a +1 charge in the product. Let's go ahead and take a look at some species like water that can do either gain or lose a proton. So if it acts as a base and gains a proton, the conjugate acid of water is the hydronium ion, H3O, with a +1 charge. If it acts as an acid and loses a proton, the conjugate base of water is the hydroxide ion, OH, with a negative charge. There are other species that can be amphoteric or amphiprotic. Either term describes this. If you have a bicarbonate ion acting as a base and gaining a proton, it becomes carbonic acid, H2CO3, with no charge or a 0 charge. If bicarbonate loses a proton, the conjugate base would be just the carbonate ion, CO3, with a -2 charge. So this is a skill that you should be able to do, giving the conjugate base or the conjugate acid of a formula or of a molecule that is being drawn. So this next section over here starts off with a list of strong acids and strong bases. None of these are organic molecules. We are going to be using some of these to do reactions with our organic compounds, so it's good to keep these in mind. So there's not that many that exist. We just have hydrochloric acid, hydrobromic acid, some sulfuric acid, nitric, hydroiodic, and perchloric acid, and then a lot of different hydroxide containing bases, lithium hydroxide, so the group 1 metals, group 2 metals, the hydroxides of those metals. So these are strong electrolytes. They dissociate completely into ions when they dissolve in water. So we could do a little practice calculation. It's definitely a lot easier to calculate the pH and the concentration of strong acids and bases because you can count on them being completely dissociated. So let's just take a look at what happens when you dissolve a strong acid in water. So here's a situation where we start off with some HBr, we put it in some water, and it is entirely going to H+ ions and bromide ions. So hydrogen ions and bromide ions are what is in the aqueous solution, not HBr molecules. They've completely dissociated. So if at the start you have 0.34 moles of hydrobromic acid, or hydrogen bromide, I suppose, then at the end, once you've dissolved it in water, none of the hydrogen bromide is left. It has all dissociated, and so you now have 0.34 moles of hydrogen ion and 0.34 moles of bromide ion. So if you do have that 0.34 moles of hydrogen ion and it's in 0.68 liters of solution, then you can calculate the molarity. It's 0.50 moles per liter. And then from this concentration of hydrogen ion, you could figure out the pH if you wanted to. So in lab, you might be using mass. So just a little review of stoichiometry calculations. So if you have 5.99 grams of lithium hydroxide, you would need to convert that to moles using the molar mass. And hopefully you remember how to get the molar mass from the periodic table, but a mole of lithium hydroxide is 23.95 grams of lithium hydroxide. And for every mole of lithium hydroxide that you put into water, you actually have 1 mole of hydroxide ions. It completely dissociates. So there's a 1-to-1 relationship there. And since we want to calculate the concentration, let's get the amount of solution in here as well. So it's 5.99 grams of lithium hydroxide it's in 1.25 liters of solution. You could always do this later as a separate step, but let's go ahead and just do it together. So then we have the grams canceling, the moles of lithium hydroxide canceling, and so then we end up with 0.200 moles of hydroxide ion per liter of solution. We have 0.200 molar hydroxide ion. In contrast to the strong acids, weak acids only partially dissociate into ions. So we have this equilibrium. Instead of having a one arrow, like a forward arrow only, we have an equilibrium back and forth of acetic acid and water going to acetate ion and proton, H+. It's just helpful to remember that if you are in water, the proton is not going to be hanging out alone. It's going to be stuck to another water molecule, making a hydronium ion. Usually it's easier to just think about acetic acid losing a proton as this type of reaction down here, that it just is losing a proton and becoming acetate and a proton. If you are in water, the proton actually exists as H3O+. So whichever way you prefer, I think this one down here at the bottom is easier, just to watch protons falling off of acids rather than worrying about where they end up, that they end up attached to a water molecule. But in any event, this is an equilibrium. Most of the acid stays together. Only a very small amount dissociates. So in contrast to the strong acids, for weak acids, you are mostly not losing a proton. You're only a little bit of it, only a little bit of the proton is being lost. The same thing with weak bases. Most of it stays alone, I guess, without having grabbed a proton, and only a little bit grabs a proton and becomes the conjugate acid. So for acetic acid, if you put 0.25 moles into 1 liter, it's not going to become 0.25 moles per liter like it would if it were hydrochloric acid or hydrobromic acid. Most of it is going to stay together, and not too much of it is going to become H+ or H3O+. So we have less than 0.25 moles of H3O+ in that liter of solution. So since we have a reversible equilibrium, we have an equilibrium constant. Instead of calling this KEQ, we usually call this the Ka of an acid. So again, this is a matter of preference, whether you want to think about the hydrogen ion or whether you want to remember that it is associated with water and it's actually a hydronium ion. The Ka value is going to be the same no matter how you write the reaction here. We mentioned that most of the acetic acid stays together as the reactant and not much of it becomes the product. So if we have a small number in the numerator and a large number in the denominator, we're going to end up with the answer being very small. So a lot of these values are fairly small. For acetic acid, we have 1.7 times 10 to the negative 5. So remember, that means it's a very, very small number, 0.000017 is the value for that. So that's a very small number. So the larger the Ka, the more the product means that you've lost the proton. So the stronger the acid, the larger the Ka. So which of these is a stronger acid? Let's go ahead and do this problem over here. We're looking at the Ka values and we see which one is larger. In contrast, we have 4.3 times 10 to the negative 7. Remember to look at the whole number, including the exponent. 4.3 looks like it's larger than 1.7, but 4.3 times 10 to the negative 7 is 0.00000043. So this is a smaller number, and the larger number is the one for acetic acid. So acetic acid is a stronger acid than carbonic acid here, H2CO3. Now for bases, we're just going to use the acids and use the factoid that the stronger the acid, the weaker the conjugate base. So acetic acid has a weaker conjugate base. The weaker acid here, carbonic acid, has the stronger conjugate base. So bicarbonate ion is going to be a stronger base than acetate ion. Okay, so these powers of 10 can vary quite a bit, so we might talk about this on a log scale. Instead of dealing with Kas, we're going to look at pKas. pKas are the negative log of the Ka value. And because of that, since it's the negative log, the larger the Ka, the smaller the pKa is going to be. So mathematically, larger Kas are going to give us smaller pKas. So larger Kas will give us smaller pKas. Let's try calculating a few of these. If you take the log of this on your calculator, you get negative 4.76. Then if you take the negative of negative 4.76, you get just 4.76. And then if you take the log of 4.3 times 10 to the negative 7, you get negative 6.37. Take the negative of that and you get 6.37. So we already knew before that acetic acid was a stronger acid because this is a larger Ka value, and then it also has a smaller pKa value. So the stronger acid has a larger Ka and a smaller pKa. Since we're talking about pKa, which is a log, let's do a little bit of a math review so that you can estimate a pKa from a Ka if you wanted to. As a reminder of what log means what power of 10 do we have here? So if we have 10 to the negative 5, what power of 10 do we have here? We have negative 5 as the power of 10. Now 1.0 times 10 to the negative 5 has the same value as 10 to the negative 5. It has a little bit more precision. So saying something is 1.0 times 10 to the negative 5 sounds like you're a little bit more sure than just saying, oh, it's about 10 to the negative 5. So this has an interesting result in the significant digits. So we could put negative 5, that's the power of 10. And for logs, the places that come after the decimal are the significant digits. So the negative 5 is what's before the decimal. The 1.0, the two significant digits that we have here, are after the decimal. So negative 5 is the answer. That's the result of what the log of that number is. But now we can put a few more significant digits there. Then if we have the negative of that, that would be 5.00. So just to show you something a little bit interesting about the significant digits, let's compare. All right, so taking a look at my calculator, this is actually negative 4.77. It's negative 4.7695. So let's do negative 4.77. So we have the power of 10 as negative 4, and then 0.77. Those are your two significant digits here. So this is actually negative 4.89. these digits in back of the decimal are what's changing. If we just change this a little bit, it probably would only change the second one. And this comes out to be negative 6.77. So when we keep this negative 5 the same, what stays the same is what's in front of the decimal. These two digits over here affected these two digits after the decimal. When we kept the 1.7 the same for this one over here, then what stayed the same was the stuff after the decimal. The 0.77 is what stayed the same. And what was different was the number in front of the decimal. So when the exponent was different, what changed was the number in front of the decimal that changed. So the term is related to the numbers after the decimal. The exponent is related to what's in front of the decimal. So that's just something kind of interesting about logs here. Let's go back to what's actually in the note packet. We know that if the Ka is 1.0 times 10 to the negative 5, then the pKa is 5.00. Like we figured out before, the negative log of this number is 5.00. The negative log of 1.0 times 10 to the negative 4 is 4.00. So since 1.7 times 10 to the negative 5, or it's a little bit smaller than 1 times 10 to the negative 4, it's a little bit larger than 1 times 10 to the negative 5. So it's in between these two numbers. Then the log of this, or the pKa of this value, is going to be in between the pKa of these two values. So it's going to be somewhere in between 5.00 and 4.00. And it says not to calculate, but we calculated it up above here. When we did the previous problem, we know that it was 4.77. So it is in between 4.00 and 5.00. So the pKa refers to the property of the acid. So it's a property of a certain acid. Whereas the pH is what you can measure about the solution. So to use a little comparison here, let's draw a comparison between losing a proton, so how acidic something is, and how hot somebody runs. So how likely are they to take off their jacket or take off their sweater? So that is a property of a certain person. Certain people run hot and they hardly ever wear their jackets. Maybe you know people that you've never seen them in a jacket at all. Whereas other people run cold, and so they are always trying to put on a jacket or put on a sweater because they just get cold very easily. So that is sort of like the property of the person. So a specific person might either run hot or run cold. How likely are they to take off their jacket? It's kind of related to pH, because pH is like the environment. So that's like the room temperature, so the temperature of the room. So if you raise the temperature of a room, more people are going to be taking off their jackets. Again, the people who run hot are going to take off their jackets first and are more likely to take off their jackets, but raising the temperature of the room is going to make everybody take off their jackets. Lowering the temperature of the room is going to make more people put back on their jackets. Again, depending on the person, you can have a pretty good guess of who is going to put on their jacket first or who's going to take off their jacket first. But the pH is the environment, so it's like the temperature of the room, and the pKa is the property of the acid, like how hot or cold somebody runs. Okay, so let's take a look at the pH of these different solutions. Again, they're a measurement of not really temperature, that's just the comparison, but they're a measure of how much hydrogen ion is around. So if we have 2.8 times 10 to the negative 9 molar of hydrogen ion around, the pH is the negative log of that, and that's 8.55. So acidic is something that is less than pH 7, basic is higher than pH 7, 8.55 is higher than pH 7, so it is a basic pH. 8.4 times 10 to the negative 3 molar concentration of hydrogen ion means that the pH is 2.08. That is lower than 7, so that is acidic environment. And finally, the concentration of 6.1 times 10 to the negative 5 gives a pH of 4.21, and that is also acidic. Many textbooks, including the one that we are using, list the pKa of water as 15.7. A lot of alcohols have pKa's around 15-16 range. Water itself has a pKa of 14.0. So your textbook even tries to explain and justify having the value of 15.7, but it is not correct. It should be 14.0. And I do have a video online that discusses how this confusion came about. Okay, so we went through this process before where we were trying to figure out which side of an equilibrium is favored. And when we did that, we went through this three-step process. We labeled the acids and the bases on both sides of the equilibrium. There should be one acid and one base on the left, one acid and one base on the right. Then you can decide which of these acids is stronger. Maybe you're given the pKa's of this, or there's a couple pKa's that we're going to try to learn. And so you'll be able to figure out which one is stronger or weaker. And then once you have the acids done, you can do the bases, knowing that the stronger the acid, the weaker its conjugate base. And then the equilibrium would favor the weaker side. We're going to first label the acids and bases. So phenol going to phenoxide, that is losing a proton. That makes this an acid and this a base. Bicarbonate going to carbonic acid is gaining a proton, so that makes this a base. And then this would be the conjugate acid. Now we can stop and check ourselves. Do we have an acid and a base on each side? Yes, we have acid and base on the left. We have an acid and base on the right, so we're looking pretty good. Now we're going to go ahead and figure out which one is the stronger acid. So we have some pKa's here. Phenol is 9.9, carbonic acid is 6.4. So remember, the stronger the acid, the smaller the pKa. So that makes carbonic acid a stronger acid. Then phenol would be the weaker acid. The stronger acid has a weaker conjugate base, so carbonic acid is stronger. That makes the bicarbonate ion the weaker base. And for the same reason, the weaker acid, phenol, would have the stronger base. And then the final step is that the equilibrium will favor the weaker side. So remember, when you've labeled weaker and stronger, both the weaker should be on one side and both the stronger should be on the other. If you have 3 weak and 1 strong, or all of them strong, or 3 of them strong and 1 of them weak, then you have to look at it again. You should have 2 weaker ones and they should both be on the same side, and then that would be the side that is favored. So what that means is that if you mix phenol and bicarbonate together, it's going to stay as reactant. It's not going to make product. That's what this next question is asking. If you want this reaction to go, if you want to make phenoxide, then using bicarbonate is not a good idea because it's just going to stay phenol and bicarbonate. It's not going to make any of the phenoxide ion, or not enough, not very much of it. So the answer to this is no, it would not proceed to the right, it stays as the left. How far the left would it stay? You can take a look at the pKa values of the reactant acid and the product acid. Let's do that for the problem above. We should have, this is actually 2.9.1. So our pKeq is the pKa of the reactant acid. That's phenol, that's 9.1. And then we subtract the pKa of the product, that's 6.4. So that gives us 2.7. And then the second equation, the Keq, is 10 to the negative pKeq, so it's 10 to the negative 2.7. And then if you put that into your calculator, you find out that this corresponds to 2.0 times 10 to the negative 3. And so that's relatively small. And remember, a small Keq means it's mostly reactants, which agrees with what we found before. We found that it favors the left side, which is the reactant side. So these two pieces of information are in agreement with each other. The reaction does not go very well. It favors the left, and it's mostly reactants. So hopefully the talk about pKa and equilibrium constants and pH was somewhat familiar. Let's take a look at some organic compounds that you might not be as familiar with. What acts as an acid and as a base as far as organic molecules go. We have this COOH group, like acetic acid. So we have a carbon here, 2 oxygens and a hydrogen, COOH. You may have seen this before, attached to some other piece. So this could be attached to other things besides just a CH3 group. And then this group is very acidic. It's called a carboxylic acid. A base can take a proton away from this. So this is an acid. It gives up a proton, and it ends up with a negatively charged oxygen. We took a look at this earlier in the chapter when we were talking about resonance. This negative charge is actually shared partly by this oxygen and partly by that oxygen. It makes it very stable. So since this product on the right-hand side is very stable, that makes this reaction fairly easy to do. So carboxylic acids have pKa's close to around 4 or 5. Amines can act as bases. We mentioned that as well. These nitrogens, when they have 3 bonds, they have a lone pair. That is an electron-rich area, and so it can be attracted to a cation like a hydrogen ion. And so this lone pair can form a bond to this positively charged hydrogen and make an ammonium ion. This is the conjugate acid, so we have the pKa over here on the acid side. This is a weaker acid than acetic acid is. So we talked about water having a pKa of 14. Alcohols have a pKa slightly higher than that. They're a little bit less acidic than water, but they have pKa's in the range of 15 to 16. So it's a little bit more difficult to deprotonate them, but you can actually make the conjugate base even in aqueous environments. Something you cannot do in an aqueous environment is to deprotonate a compound like acetone. So pKa of in the 19 to 20 range is not something that can happen in water, because remember the pKa of water is around 14. It's much more acidic than a compound like acetone. So if you have a base, it will react with water before it will react with acetone. If you have a solvent where there's no water around, then you can get this reaction to work. The base can deprotonate some acetone. We're not going to memorize a lot of pKa's, but we do want to at least get these. They're really very common benchmarks. So carboxylic acids, knowing that they are in the range of 3, 4, 5 as far as their pKa's go, is very important. We also mentioned amines. Once they're protonated, they have a pKa in the 9-10 range. and then water is 14, alcohols are 15 or 16. And then we do have some very strong acids. We don't usually talk about the pKa of strong acids because they completely dissociate. And then there are some protonated intermediates that we're going to be working with later in the course. And so these could be very, very strongly acidic. So the pKa would end up being less than 0. It would be a negative number because the reaction lies so far to the right. It's so much, it's pretty much completely dissociated. So let's look at these. This is something that you should be able to do just from your knowledge without having the pKa's provided to you. So this is something that you should learn, that the pKa of a carboxylic acid is around 4 or 5. Let's go ahead and write that down. We'll just say 4. The pKa of an alcohol is around 15 or 16. Let's just go ahead and say it's around 15. And then an ammonium ion, a protonated amine, the pKa is around 9 or 10. Let's say it's around 10 here. And remember that the strongest acid is the one with the smallest pKa. So this is the most acidic. Then comes this one. This is medium. And then the largest pKa value would be the least acidic. Okay, so we have an unfortunate page break here, but the most acidic compound from the bottom of page 25 is going to give the least basic conjugate base. So this is the most acidic. That makes this the least basic of these 3 possibilities. This was the least acidic, and so the conjugate base is going to be the most basic. And then the ammonium ion was in between. That makes the amine in between these as well, so I'll put medium. All right, let's see if we can use our knowledge of acids and bases and pKa's to answer a couple of questions here. So if we have water, H2O, we know that pKa is 14. And then we're going to look at acetic acid. So this has been 4.77 is what we've been using for the pKa value, but we'll say it's just like around 4 for a carboxylic acid. And so acetic acid is more acidic than water. So if the two of these react together, acetic acid is going to be giving up its proton. And so that will become the conjugate base. It will give its proton to water. So water is acting as a base. It's going to create hydronium ion as the conjugate acid. So this is what is going to happen. Okay, so what if we had this compound over here that has both an amine and an alcohol? And then if we started adding a little bit of acid, if we had some proton around, would it land on this oxygen or would it land on this nitrogen? So let's take a look. We have it landing on the oxygen over here, and then we have it landing on the nitrogen over here. So if this goes back and forth, if the proton is hopping back and forth from the oxygen to the nitrogen, which of these sides is favored? So we have this amine acting as a base, and this positively charged oxygen acting as an acid, because this is giving the proton over to the amine. Once the amine gets it, this is the conjugate acid, and then this oxygen without the extra proton is the base, because going in the opposite direction, this oxygen grabs a proton from the nitrogen. So this is acting as the base, this nitrogen is acting as the acid. Going in the forward direction, this is acting as the acid, giving up a proton to this nitrogen, which is acting as the base. So we have our acids and bases labeled. We have one base and one acid on each side of the arrow. Now we have to determine which is the stronger acid. So we have this, it's like a protonated intermediate. This pKa is way less than 0. So this is not an alcohol, this has an extra proton, so this is a very, very strong acid. This alcohol over here, in order to lose this proton, would have a pKa of about 15 or 16, but this is not acting as an acid right now, this is acting as a base. So we're not going to use 15 as the pKa, we're going to use this acid. This protonated alcohol has a very, very low pKa, it's very acidic. In comparison, a protonated amine has a pKa of around 9 or 10. So something that is 9 versus something that is lower than 0, like a negative number, this is a much lower number. This is a much stronger acid. This is a weaker acid on the other side. That makes the amine a stronger base. That makes this alcohol a weaker base. So that makes the right side favored. So between these two, this amine is a stronger base than this alcohol. So the amine is what's going to grab this proton, and it's going to end up on the nitrogen. It is not going to end up looking like this. Let's do another one of these equilibrium reaction using glycine. So if you want to try any of these for yourself, you can always pause the video and see if you can figure this out, figure out which side is favored. Does glycine look like this molecule on the left, or does it look like this structure here on the right? So here we again have a nitrogen that's positively charged. This nitrogen is neutral, has 3 bonds and a lone pair. Going from the left to the right, we're losing a proton, so that makes this an acid, and this a base. This negatively charged oxygen is gaining a proton to become the OH group. That makes this a base, and this an acid. Now our next step is to look at the two acids and see which one is stronger. So we have a pKa of a carboxylic acid being around 4, a pKa of an ammonium ion being around 9, and so between these two, the pKa of 4 is stronger. This one is weaker. The weaker acid has the stronger conjugate base, so this is also stronger. And the stronger acid has the weaker conjugate base, so this is weaker. And the side that's weaker is favored. So this amino acid, glycine, actually exists in this form. This is called the Zwitter ion form because there's 2 ions. Zwitter means both, so both of these groups are ionic. We have a negative ion and a positive ion as part of glycine. All right, let's do one more equilibrium over here. So go ahead, step by step, label the acids and the bases, then label which ones are weaker and stronger, and then decide which side is favored. So let's do the first step and label the acids and the bases. We have carboxylic acid acting like an acid and grabbing a proton, and then we have bicarbonate acting as a base and grabbing a proton to become an acid. Now we have some pKa's. We have 4.8 for acetic acid. We have 6.4 for carbonic acid. That makes this one stronger. Acetic acid is stronger. That makes this base the stronger base, bicarbonate ion. And the acetate ion is the weaker base. and then the weaker side is favored. So before we were asking whether bicarbonate would be a strong enough base to remove a proton from phenol, and the answer was no. This time we do have the right side of the arrow favored, so most of this reaction is going to end up as products. And so yes, this reaction does happen. We do get the products. So the answer to this question would be yes. We can use carbonate ion to react with acetic acid and make the conjugate base of acetic acid.